Hi, and welcome back to part 3 of lecture 32, where we've been talking about special types of adjoint operators, or special type of operators on inner product spaces. So in this part, we want to talk about what are called normal operators. Okay, so an operator is normal if it commutes with its adjoint. Okay, that means that if I take the adjoint of t and evaluate it at t, it's the same thing as first evaluating at t and then its adjoint. And every self-adjoint operator is normal. Okay, so why is that? Well, let's look at why that is. We're looking at t times or first evaluating at the adjoint and then composing it with t. Now, because this is a self-adjoint operator, we can replace t with its adjoint, and then we can also replace t with its adjoint over here. Right? And so the adjoint of the adjoint is just the original function linear operator to begin with, right? So we have this part here can be replaced with t. But so look what we have here. So this is using the fact that t is self-adjoint, gives us this statement, and then by properties of the adjoint we get this conclusion. But that's exactly what we need for normality. Okay. Again, if you prefer thinking about things about in terms of matrices, what we're saying from a matrix point of view is saying that A times A transpose is the same thing as A transpose A. Okay, so the operator associated to this matrix would be normal. And if we were looking over the complex numbers, this would be saying that A times the conjugate transpose is the same thing as A star A. Okay, so that's kind of the matrix point of view. Okay. Now, one nice thing about normal operators is that they have the property that t and its adjoint send a vector to the same norm. Okay, so t and t star send v to um, vectors of the same norm. So TV and T star V may be different vectors. They may be completely different vectors, but they have the property that those new vectors that you get have to have the same norm. And if you're comfortable with the notion of length, if you're thinking about this kind of geometrically, it's saying that T and T star send vectors, any vector to new vectors, and those new vectors have to have the same length. Okay, and let's kind of walk through the proof here. Okay, so what does it mean to be normal? Well, one way of re-expressing the normal condition is saying that this operator is the zero operator. Right? I've just rearranged the definition up here. Right? So I'm just rearranging this statement about operators. Okay. Now, because this is the zero operator, that's the same thing as saying that if you take this operator and evaluating at v, comma v, you're always going to get 0 for all vectors v and v, because this first entry is 0. Now, using properties of the inner product, we can kind of expand out and rearrange. So on this side, we get t, the adjoint v, v, minus the adjoint of t, v, and v. Okay, so I'm just rearranging this on the left-hand side, and that's equal to 0. Now we use the property of adjoints. So we can move this t over to the other side by taking its adjoint. And same thing over here. We can take this t star, the adjoint over here, and move it over to the other side by taking its adjoint, right? So we get tv, and then you get the adjoint of that guy equals 0. And notice that this here is actually the t, right? So, okay, so let's clean that up. So that's equal to 0. But now, we haven't used our normal condition here, Well, no, actually, that's not what we want. We wanted to show this statement right here, right? So the first statement here, well, that's just the norm of this guy squared, and this guy over here is the norm v squared. And because these guys are always positive numbers, right, this is just telling me that the norm of TV is the same thing as the norm of the adjoint evaluated at V. Okay, so there we go. That finishes off the proof. Okay, so that's one nice thing about normal operators. These are precisely the ones that kind of preserve norm. Uh, the normal operators are the ones where the operator and its adjoint have preserved the norm. And the other nice thing about normal operators is that if you know the eigenvalue of t, and if t is also normal, you actually get for free an eigenvalue of the adjoint. Okay, and I'm going to start the proof, and we'll finish the proof in the last part. Okay, and the way to make this proof work, and I don't think this was actually done in complete detail in the textbook, but I thought I would do it for you, was you have to first start with the claim that if you take any, this is any value, lambda, so this is any number inside of my field f, and if t is normal, then this operator, t minus lambda I, is also a normal operator. Okay, so let's walk our way through our proof. So we want to show that the order of these operators can be switched around, that they commute. So in the first stage, I'm just using the properties of the adjoint to move it inside of the brackets, right? So I move it inside the bracket. It's just the adjoint of t times the adjoint of this operator. Now continuing on with the properties, I'm not touching the first operator. This still stays the adjoint of t, and this becomes the conjugate of the eigenvalue, and this becomes I star. Okay, the adjoint of the identity operator. But remember, the adjoint of the identity operator is just the identity again. So we could rewrite this as t minus lambda I times the adjoint of t minus the conjugate of lambda times I. Okay, and maybe I'll put that there. That since I is equal to I star. So now we expand out this operator, and this is equal, and you got to remember to keep the order in the right order. So we have t times the adjoint of t, and then we have minus the conjugate of lambda times t times I, and on this side, continuing on using our FOIL, we have minus t, well, I guess I, t, the adjoint of t, and then I end up with lambda, its conjugate, and then I squared. Okay, so that's what we have here. Now there's a couple things now we can use going forward. Is notice that t is normal, so we can switch the order of this guy. So this is t star, the adjoint of t times t. We can, because the addition of operators can be moved around, that's fine. So we can actually, and because it's the identity operator which commutes with everything, we can, our next term can be lambda adjoint of ti. We'll move this the second term into the third spot, and we'll switch the order of the I and the t, and then we can switch the order of the constants, that doesn't matter, and then we have I squared. And you can convince yourself that this is the same thing as expanding out t star minus the conjugate of lambda I times t minus lambda I. Okay, so we get the exact same result that we had before. Okay, so just remember here, from here to here is where we use our normal property. Okay, so this was actually just the first stage of the proof. I'm going to pause here, and then when we come back, we're going to finish up the proof. And as I said, I don't think this particular piece was actually in the textbook, so I wanted to expand that out for you.